Dr. Massoud Amin, IEEE and ASME Fellow, is President of Energy Policy and Security Associates, Professor Emeritus of Electrical and Computer Engineering at the University of Minnesota, and a University Distinguished Teaching Professor Award recipient. He is widely credited as being the father of the smart grid and a cyber physical security leader who led the development of 24 technologies transferred to industry and directed all security-related research and development for all North American utilities after the 9/11 tragedies. In fact, he was actually at a meeting less than a mile from the Pentagon discussing disaster risk management with the White House Office of Science and Technology and DoD officials right when the terrorist attacks took place on September 11th. So with that, Dr. Amin, thanks for joining us tonight, and it's all yours.
Thank you, Dr. Turgeson. I'm honored to be here. Thank you for the invitation, colleagues from the Climate Reality Project and the Central Minnesota chapter. In the next 15 hours, I will be honored to share with you what's going on in microgrids. I hope you're ready. So as we think about the transition, energy transition, and more specifically, the most efficient form of transfer of energy, which is electricity, not hydrogen, not storing it as fossil fuels or burning with them, but electricity is the most efficient carrier of energy. Electrons are the most efficient carrier of energy. Where are we, specifically when it comes to microgrids, which is a subset of smart grids, and what are we doing about it? And what are some of the challenges and opportunities as we go forward? I'm going to also share with you some examples from Minnesota that have been successful and some lessons learned. I hope that's okay. Thank you, Natalie, for arranging this. I asked Natalie about the audience, and these are some of the key good feedback that I had from Natalie, that the members are advocates for the areas you're seeing here, climate change concerns, as well as adopting better, more sustainable, clean energy policies and implementations, as well as some of the colleagues who have gone through Vice President Al Gore's climate reality leadership training, and you see the rest. The key is the bottom three items. What is the microgrid? What are the benefits? And what can you do, if anything, which I believe you can do quite a bit in Minnesota, in our region, nationally, and perhaps globally, depending on which organizations you get active in. So I will share those with you. Before I go into the details of it, I want to first start with the big picture. In 2000, Neil Armstrong was appointed the chairman of a Blue Ribbon Commission at the National Academy of Engineering to look at the greatest achievements of engineering in the 20th century and chart, if you will, what is to come, and do we have the workforce, do we have the capability to execute them? When he was appointed, I remembered watching him on a black and white German-made Grundig TV walking on the moon. So I thought, oh, it's a done deal. It's man walking on the moon. However, that was number 13 in the list of the top 20. Number 1 was the North American power grid. If you kind of take a moment, take a deep breath, and you think about it, everything we are using today, not just our electric and electronic devices, but our quality of life critically depends on reliable networks of electricity, as well as on communication systems. Those are the two fundamental infrastructures out of 16 critical infrastructures we have in our nation and globally that underpin everything else. So how did we get here? If you look at the transition, and thanks to Dr. Kunin at EIA, we have substituted different forms of energy, different sources of energy in the last 170 years. We have gone from primarily wood in dark brown, a little bit of coal, substituted other sources, hydropower through dams, Niagara Falls, the first large one, oil, natural gas, nuclear power, and renewables. Renewables is increasing, and I will share with you that journey. This substitution also comes with quite a bit of subsidies given to the producers and the developers and others, as well as technologies and human capital workforce that is in there. If you look at this history more recently in the 20th century up to about 2012, you will see the transition that started beginning initially with the parts that you're seeing here, hydro dams, and then we had coal, and then we had oil, and after that nuclear kicked in yellow, and then we have more natural gas, and this is the peak, most of it West Coast California before the energy crises that we had in California, because it was easier to get siting, building plants for natural gas, connecting it to the high voltage transmission and bringing it to population centers and byways along the way. And then more recently, wind and solar, geothermal, biomass, other sources have kicked in. So back then, up to when I was born, 1961, it was our capacity was we needed about 186 megawatts. It increased to 250 megawatts in the subsequent decades and kept increasing as our technology, as we use more electricity and population grew. If you look at how many people did it support at the time, it rose from 92 million to over 300, now over 330 million as we talk today. So it underpins everything we do. Step a little bit further out. We had 2 years ago, 3 years ago almost, we had 30 mega cities with 10 million or more people in them. By 2050, even conservatively, according to the UN and other population studies, this is going to double. We are going to have 60 such cities, most of them in underdeveloped or less developed parts of the world. That increased population needs even for more resources, energy resources. And we are already, we have seen the climate impact of our past choices the last 150 years, where it has gotten us. What we did in the past is not going to be a good solution going forward, especially since we are going to need to triple the amount of electricity, approximate, and this is conservative approximation, tripling that. Data centers, digitizing everything, even Twitter have it, and I've analyzed this, I've written, published on that. How much does it cost? Twitter, just by itself, takes 5 large nuclear power plants a year globally to keep all the things we upload to Twitter. There's a lot more we can talk about. Now, please, if you would please close your eyes, take a deep breath. Think about 3 major concerns we have: environmental security, national security, economic security. First of all, do these 3 intersect? National security, economic security, environmental security. And if they intersect, what's at the nexus, at the intersection of all 3, that if we address it, it's going to put a major advancement, major benefit to address all 3? Energy security, I submit to you. There is no silver bullet, but there are many innovation bullets that alone by themselves, they will not succeed. We need to consider supportive public policy, advocacy, public education, as well as new technology development and integration into the system. Stepping back even further, if you think about our development of human history, from around hunter-gatherers used 2,500 calories a day per person to sustain their life. Agrarian society farming, when we evolved into that, each person used about 4 times that much, 10,000 calories. Industrial started with about 50,000 calories per day, but with all the flights that we do, with all the equipment we use, even though efficiency has improved in the last 40 years, but we use up to 600,000 calories per day per person. So the challenge is, how do we move forward in a sustainable way that addresses the environment, addresses national security, and economic security? And my background is in electrical and computer engineering. I worked on aircraft for the US Air Force, also for Air Mobility Command Transcom from 82 to 97. And in 97, I moved to Electric Power Research Institute as the head of mathematics and information sciences to use the same type of thinking to make our power grid, end-to-end power grid, assessing that, understanding what are the weak links, strengthening them, and modernizing it. What at the time I called smart self-healing grid. So we're going to look at it end to end, from sources and how we bring it to enable the quality of life that we have today and more. But we are in the midst of an energy transition. We are moving from what you see on the left-hand side of the screen, fossil fuels, long distance, Tesla's dream of generate large amounts far away from population centers, use high voltage transmission lines, 100,000 volts and higher, and bring them to population centers and smaller towns along the way, and then bring it down to the level that consumers, industrial, commercial, residential can use it. We're moving more into integration of renewable energy, on-site generation and utilization, zero energy buildings that have zero footprint or near zero footprint in greenhouse gas emissions. And we're not going to cheat. We're going to look at the whole system. Many people, you have seen that with electric vehicles. Yes, the vehicle itself is much more efficient. But if you look at the whole supply chain from cradle to grave, what's the footprint it puts, manufacturing that? We go through all of that. So to enable this transition in a responsible way, in a science-driven, technologically savvy way, we're going to look into smart grids and microgrids. At the same time, given our history, the system that we operate, this North American power grid, marvel of the 20th century technology, is being, in some ways, becoming a relic of the last century. The average age, sunken investment is about $1.3 trillion into the system. Most of it on the generation and high voltage kind of transmission, but most generation. And average age is 40 to 60 years old. I'm 62. And I admired, of course, the space program, aircraft, many things about America before coming to the US in 1978 for my senior year of high school in New York, from Iran, from Tabriz, Iran. But as I witnessed the New York City blackout in 77, I realized all of those would not work without electricity. The crises that happened in New York, and I've given TED Talks, other things on that. If you're interested, colleagues who may watch it later on your YouTube channel, you're welcome to check them out. And about 25% of these assets are of an age that their condition is of a concern. So you look at the trends now, transitioning from big picture to details. The trends you're seeing on the screen are just a few highlights. I will share a little bit more detail into that, but basically resiliency, especially with the, to give you a context, I've analyzed outages in North American power grid. From 1950s to the early 80s, mid 80s, we had only 3, 4, maybe 5 major outages affecting 100 megawatts or more, caused by weather. That number, oh, by the way, that used to be root cause number 3 or 4 at the time. That number started changing in the mid-1990s, early 90s. And now it has risen from 3 to 5 to 137 weather-caused major outages per year in the United States. And that is, by the way, adjusted for population growth. So the root causes are aging infrastructure and climate change, without a doubt. So reliability and resilience are huge. Resilience, I mean being able to take hits, but the system will not go down. You may have local failure, but you won't have systemic failure. And there are many other rulings. Good news is there has been investments in the bringing electricity in, and many sources actually now have transitioned from coal into natural gas and into renewables into the whole system. So the chart you're seeing is accurate as of 3.5, 4 years ago. And that these are regions of our nation that are under the control of different control centers. And if you look at these trends, and this is part of the report that I had the privilege of, there were 6 chapters in it. I had the privilege of preparing chapter 4 on aging infrastructure, how to modernize it, how to make it more resilient and secure, and upgrade it about 6 years ago, the last year of the Obama administration. And it has now, thank goodness that it has come back as part of Infrastructure Investment and Jobs Act, as well as Inflation Reduction Act, which I won't get into tonight, but if you're interested, I have also material detailed on those, what we have done in that area and what we are doing. So these are some of them. And also many asset owners are not sure about return on investment, especially given the low rates, and public generally doesn't appreciate reliability. And on any given day, we don't have outages. We have a pretty reliable system. But however, with adverse weathers, that has increased. The average cost of outages per year that don't include matter, that just based on external events, is somewhere between $80 billion a year to US economy to over $183 billion a year. So DOE and the White House have approximated it roughly between $100 to $150 billion a year. And that's part of that increase that I mentioned. And there are also other severe weather events that I mentioned, physical cyber attack, also interdependencies. These are all dynamical systems, but power connects also both way, bi-directional connection, with fuel supply, with transportation, with water supply, with telecom, environmental impact, markets. That's why you see the prices when there's a choke point in transmission, prices go through the roof in one pocket or a region, as well as recovery of investments and policy that would enable that without breaking the consumers back. So to frame it, these are the actual drivers. Acceleration of efficiency. Good news is that has been going on relatively well. Former Secretary of Energy during Obama administration, the Nobel Prize winner in physics, called it, it has been such a the area of efficiency, we have been working on it since the 70s. To give you an idea, coal-fired plants at the one end are about 35% efficient. If you put carbon capture on it, it takes energy. So the efficiency of turning coal into burning it and turning it through turbines into electrons reduces the efficiency by about 1/3, drops down to about 26%. High voltage transmission is 97% efficient, as long as you don't overload it. That's the beauty of Tesla's original dream. Nikola Tesla was right. That was at the time the right way to do it. Do it away from population centers, put it through highly efficient networks, and those are alternating current. If you do DC, direct current is even more efficient. And we don't talk too much tonight about DC, but that a lot of microgrids, because at the end use, our computers, our digital devices are using direct current. So what's the point of alternating AC to DC when you can do the whole system DC? Back then, Edison's dream was everything DC and microgrids, local grids, local area grids. However, to do that, you had to run a wire from every generator to every device. It was like a bowl of spaghetti back then that you didn't have the electronics, controls, instrumentation to do it in a way that you wouldn't have all these wires running everywhere. Now we do. So I won't get too much into it, but that's another major trend in conjunction with smart grids and microgrids, which is worthy of consideration, changing especially the whole building or the whole home being DC. So then DGs, distributed generation, distributed energy resources, storage, microgrids, and so on, and cities that are interested in having their own microgrids or different combinations from substations to major population centers being its own as self-sufficient as possible, microgrids and so on, and district energy systems like what we have in St. Paul, Minnesota, as well as in Rochester and other cities across the world. And then a smarter grid that has the overlay of communication, sensing, control, automation to make it more efficient. I'm not going to give you the whole presentation on smart grid, but if you're interested, think of it as an overlay of automation with security built in, computation, control, information, intelligence that enables more reliable, more secure, more efficient operation and control of the entire system, and integration of renewables into it. Also, you can send prices to devices, makes it a lot more smarter. For those colleagues who are familiar with Department of Defense, this came out of my own work for DoD called C4I systems: computation, control, communication, command. Those are the C4 intelligence or information. C4I overlay as a network over that. You can apply that over supply chains, you can apply that over battlefields, over logistic networks, transportation networks to make them smarter. And I did it for the end-to-end energy connected to communication, transportation, markets, and the environment. And then transportation being electrified, EPA regulations for emissions such as the Clean Air Act, demand response, and there are some other non-utility stakeholders that have gotten into it and are collecting the smart meter data and extracting intelligence out of that and selling it or reselling it and using it to those who want to automate. And then combine heat and power that makes it very efficient. Going back, this is what I was waiting for. That coal-fired power plant, let's say 35% efficient without carbon capture. The high voltage 100 kV and higher, 100 kV, let's say to 800 kV, that is 97% efficient. Distribution system, so from 100 kV, which is the bottom of the high voltage transmission, you step down to 60. To, let's say you have others 30K, etc., but let's say 15K below is considered distribution network. Some major industrial customers, manufacturing, car, etc., use that level of current and voltage. That's what they use. However, in between, we call it sub-transmission. So high voltage transmission, sub-transition, transmission, and distribution systems. Distribution, you can think of it end use and customers. So when you combine high voltage with distribution, so the transmission, T&D distribution, the efficiency of that, of course, depends how much you have loaded the system, if there are any thermal losses in the system, or is this theft? When you travel in developing parts of the world, you see wires running all over the place. That's unauthorized use. That's theft. So the efficiency without that theft is about 91% for the wires part. The end use, incandescent light bulb, as amazing of a limit-breaking innovation invention that was from Thomas Edison's laboratory, it's only 3 to 5% efficient. Of course, in Minnesota, we don't mind because we are cold half of the year. So that heat is part of energy losses. Whatever you do that is not the intended use, that's loss of efficiency. For example, you want light to illuminate, not to be a heater. So LEDs are about 10 to 12 times more efficient. That's why holiday season, the lights that we use for LEDs and so on are more efficient than what we had. So if you multiply, please take your smartphone or on paper, multiply the efficiency of the coal, 0.35, times the wires part, which is, let's say, 0.9 on the conservative side, times 0.05 for incandescent light bulb. That would give you end-to-end system efficiency. What number do you get? If you multiply 0.35 times 0.9 times 0.05. You see, I'm a retired professor, so I have to give you a pop quiz. Any good Samaritan who would unmute and answer that, please? You're going to get about 1.6 to 1.8% efficiency. Did you know we are wasting over 98% of the energy that is in that coal? If you want to do natural gas, so replace that. Instead of 0.35, replace it by 0.4, 0.45 for natural gas efficiency. The end use, if you don't want a light bulb, look at the back of your air conditioner, refrigerator, whatever device, what's the efficiency, multiply it. On average, we lose about 70% of energy content in the current way we run the system. By the way, one point that I forgot to mention here, if you look at this system, there's another dimension to it that is really timely to talk about it. So we moved from hunter-gatherers to harvesting, right? Then we moved to industrial. In the process of that, guess what we did? We went in the business of drilling holes, exhausting the resources of these holes, and moving on to the next hole. And in doing so, there is a geopolitical national security aspect, is we become bedfellows with governments and systems that don't have our interest in mind. And remember the oil crisis of the 70s and so on. So it gets really messy. Or we can get into the politics of it, invasion of Iraq and other things we were promised or we are told that the oil prices will go down and so on, and it didn't. And please put that as Massoud Amin's personal observation as an individual, as a US loyal US citizen, rather than as an expert. So this is not sustainable from many points of view. So as we move forward, this whole system can become more efficient even with the old part if on coal, natural gas, you put combined heat and power, because you capture some of the heat which is lost in the generation, you feed it back. So that 35% efficiency can go up to about 75% efficiency. However, cost of doing all those docks and tunnels and so on is expensive. If you look at St. Paul Power District, they have that. They generate heat and hot water out of that. And Tim is very familiar with all of those sources in Minnesota and beyond. So there's also more that we treated like a national grid, like a whole interconnected system, rather than 4 subgrids. Currently, we have everything east of the Rockies, except Texas and Quebec, is one interconnected system. If somebody, let's say major load goes on, we all turn on our lights, a generator typically nearby goes a little bit faster to meet up with that demand. Then everything west of the Rockies, 11 western states and 2 Canadian provinces are the western interconnection. And then in Texas and Quebec, the electrons have a Texas accent or a little bit of a French accent to keep their autonomy. They're still connected. All these 4 major subgrids are connected through DC lines for extreme contingencies, but they're limited how much they can help each other. That's part of the reason when Texas was having the cold spell, the whole region from north of us down south to the Gulf of Mexico was going through the same shortages. There wasn't much transfer available to send through the DC lines from the Eastern interconnection or from Western interconnection into Texas. But that's another story. So these drivers define many key questions that are for utilities, for regulators, for businesses, for citizens. What business models can be developed to serve both upstream as well as the end use? what are the effects that these business models have on incumbent utilities, and what opportunities exist for other sectors to get into it, similar to what telecom went through. And with the wireless technology, we saw what happened, sadly, to some extent, to Bell Labs and Bell Telecom and other major players back then. And then how will regulation need to evolve to create a level, transparent playing fields, including what subsidies we have given to whom, and how much are we using that subsidy incentives to reduce the price of that, and has that over time with any new technology adoption. That's normal to have subsidies up front, but over time that has to be diminishing. What visions do you see for the future, and then what measures, especially for critical infrastructure protection and security of the cyber physical systems, do we have, and for especially empowered consumers? Anne Primajori formerly was the CEO of ComEd in Chicago. She has a wonderful quote, which is, "The regulatory framework is keeping us locked in the 20th century system," unfortunately, and I get more into it. So good news is I built on the shoulders of giants long before me, when they had put communication, utility communication architecture, automation, etc. I started this area in January of 1998 at EPRI, Electric Power Research Institute. And it took 9 years, partnership of many amazing colleagues from DOE, from utilities, from universities, from think tanks, to have it become law back in 2007. And this is the law that passed the Congress. It's the policy of the United States to support the modernization of the nation's electricity transmission and distribution systems. This can meet future demand growth and achieve each of the following, which together characterize a smart grid. There are 2 steps. One is, and this is the actual law that passed both Senate and the House, increase use of digital information and control technology to improve reliability, security, and efficiency of the electric grid. Dynamic optimization of the grid operations and resources with full cybersecurity. At the time, it was only a $50 million funding that went to NIST to come up with standards for interoperability. During Obama administration, I'm pleased that about $4.5 billion went into it. Utilities matched that even more, and there were so many successful implementations, and there are many reports I had written on that, assessed DOE's investments, other agencies in that. That was a great early down payment. However, it cost about $500 billion to upgrade the system into a truly smart grid. So that was a small drop. The current investment out of the IIJA and IRA investments are going to help. And it's the first time in 6 administrations that we have had this opportunity to actually make a dent into this challenge. So these are on behalf of IEEE, ASME, National Science Foundation, other stakeholders, I briefed the Congress multiple times. First time was after the 2003 East Coast blackout. You see the dates on the bottom. Unanimously, we assessed, shared our assessment collectively, and these are the 4 areas. Build a stronger backbone that can integrate large wind, solar, renewable resources that are away from population centers, put them through that 97% efficient high voltage grid, bring it to population centers. So that's the stronger. Smarter, make it smarter grid with instrumentation, controls, algorithms, machine learning. We use AI and machine learning extensively in this area since the 90s. And now with faster computation, we can even do better prediction, forecasting, and so on. Break our addiction to oil by transforming transportation, but don't cheat. To electrify transportation, but look at it from beginning to the end. Where are these raw material come from? And then greening the supply, the electric supply, renewable generation, this is, hard to believe. It was 20 years ago last week that I briefed the Congress on this. And then expand smaller, more modular Gen 4 nuclear reactors, modular, smaller, and more actually fail safe. In the worst case, they use gravity to bring water in. And then capture carbon emissions from fossil fuels in power plants, so incentivize carbon capture as we go through this transition, and increase energy efficiency, especially at the two ends where the losses are. So to give you an idea, this assessment also came from my old work when I led grid operations and planning for EPRI, for the utilities, as well as DOE and American Electric, AEP, and other utilities that helped us with this, and many utilities. So look at where the resources around our nation and just to the north of us are available, because we are an interconnected grid, Canada and US. We have areas that are shaded in gray is where energy resources are. The growing population densities are the red dots. So those are the likely directions. And if you look at it from an engineering perspective, guess what they do? Those directions of flow are for augmenting the existing system with high voltage transmission in that system. And as you see, these are all augmented in the same rights of way to make it stronger. This is the stronger part of the grid. So we have also DC as part. Most of these are DC. All of these are DC actually, to make the system more controllable and more efficient, if that makes sense. It's the DC backbone augmenting the greatest achievement of engineering in the last century, to bring energy from the far away where they are available into population centers. So now closer to home, these are the kinds of projects. Now getting to microgrids, I've had the privilege of doing at the U of M since March of 2003, and my former colleague who retired, Professor Bruce Wallenberg, also has been my partner in crime. I'm more into the computational methods, controls, automation, systems assessment. Bruce is more of a power system gentleman, and these are the areas that we have done, summarizing them in 5 bullets. And a lot of it I included here for you are from Minnesota. These are the microgrids in Minnesota that we have done. So I will fast forward. So basically the overlay I mentioned to you, the overlay of smart devices, smart agents, sensing, communication, control, security built in to automate the system, taking an old, let's say, aircraft, and instead of throwing it out, you augment the avionics, the control surfaces, the instrumentation, the display, the engine thrust, and so on, and you update it in the same way. That's exactly what we are doing. Now you see them a lot on Velocity, Motor Trend Channel, that they keep the body of the old cars, but they put LS3, LS whatever, souped up engines in them, and they change the steering and transmission. It's the same idea, basically at a larger scale. So this assessment of a microgrid, I had the privilege of doing it for after the 2003 blackout. And if you're interested, publish the paper with Dr. Paul Shuey from American Physical Society. He's a technical writer and PhD physicist, outstanding, that we showed that in my graduate students and we did the work at the U, that if we had this smart grid, self-healing grid with a faster communication, faster monitoring, look ahead, predictive control, we would have avoided the whole blackout that put 50 million people in the dark. It would have stopped in less than a minute having done that. And then we have applied it to a whole bunch of problems. However, there is no free lunch. The data, volume of data that comes out when you have such instrumentation, billions of devices that are being monitored globally, you have lots of data. So currently, let's say today, we have roughly about 80 to 90 terabytes of data at an average mid-sized utility. You put the technologies, the capabilities we have on hand off the shelf, no R&D is needed. You put these into it very quickly. And of course, you assess the impact, business impact, benefit to all stakeholders, customers, etc. Very quickly, the number goes from, let's say, 90 terabytes per year, goes to about one order of magnitude, 820, 830 terabytes of data. My colleagues from IBM, Google, elsewhere said, Massoud, don't worry about it. We can handle that. Except utilities don't have the technology, the capability to handle this volume of data and close the loop for a real-time or near real-time, let's say 5 seconds ahead, 60 seconds ahead type of use, enable this. So to give you example close to home, I'm grateful to the vice president from Minnesota Valley Co-op. He shared this slide with me. Before having smart meters are just a measuring node to measure. Instead of having a meter reader going around your home, it automates that. And people thought, if I have a smart meter, I have a smart grid. No, it's just a measurement, it's a sensing. Before that, they would read it monthly. They had 480 data points per year. After they put smart meters, they were reading it. They could read it every 50 to 60 minutes. We could also see more detailed for reliability and security and voltages and so on and power quality changes. The number grew from 480 data points per year, 1,000 times that, 480 million data points per year. A typical utility doesn't have the computational capability to do it. And most of the data that was collected or is being collected by many utilities are for post-mortem analysis or for after failures. They go back, they say what happened. So to look at this, and I'm grateful to a company in San Diego who shared this with me to share, called OnRamp. We're going to need to connect 50 billion devices. And that's only water, gas, things that are in vaults, underground, pipeline circuits, and indoors. 50 billion devices. That's a massive undertaking, and to do it securely. So part of my work and what I do at Energy Policy and Security Associates is technology assessment and triage. I will share a little bit on that. It's the function that typically CTOs do, chief strategists do, and so on. These are the 5 top areas when it comes to the material that you're interested in. Storage, together with microgrid, with cyber, and cyber is both information technology, IT, and operational technology, things that run stuff, and physical security, because of both physical attacks, increased number of the white supremacists, separatists, and so on that are shooting transformers and substations and so on, as well as the climate change, adverse weather impact, etc. And then on top of that, the overlay of advanced controls, including energy management systems and distribution management systems that would enable situational awareness and actionable intelligence coming into it, and to control the system better breakers. And then you also can do smart buildings, you can do smart college campuses, smart industrial parks, and in-home technologies, depending on and of course, to retrofit is more expensive than having it put in as part of the construction, design, and build of the property. To give you a quick footnote, if you include the wiring for electric vehicle, for solar panels, integration of renewables, it increases in Minnesota, it increases your cost by about 4 to 4.5% per home. But if you try to retrofit it, it's about 13, 14%, which is too much. So keep that in mind, please. And then big part of it is, what do consumers really want to make it into a well-managed, secure, and smart grid? So good news is, and this is from our own lab at the U, the little lab that I had the privilege of creating since 2003 with the doctoral students that I've had, that have done the work in that area. We could put gaming computers, what NVIDIA uses, and we put them in Alienware machines. The gaming that maybe your children or grandchildren use for gaming, we put 6 of these, what's called NVIDIA Tesla boards, 6 of them in one box. We could do faster than our own beloved Seymour Cray, U of M alum from my department in math. We could do faster computation than his, not even his Cray's 1990s machines at a fraction of the cost, under $10,000. And we had 4 of these workstations in my lab. And then there are, if you look at the NVIDIA GeForce GPU, we could also do this look ahead that I mentioned to you, risk assessment, reconfiguration control, 15 times faster than anything in the industry. And I'm grateful that this technology has now transitioned to industry. My students work in industry. Now, more specifically to microgrids, I like what Dr. Datagod Boli, who was at Honeywell, was a VP at Honeywell for many years, shared with me, and I got permissions to use these. Basically, think about a microgrid. You have a supply side. It can be local wind, or it can be from far away, photovoltaics. It could be even a campus that has a community solar, cogeneration, combined heat and power, like what we mentioned, other sources and biomass. And you have seen in Rochester, they're doing a pioneering work. Instead of drilling 50 holes to get the heat out of the ground, they're using the heat from water. Instead of 50, they only need 2. It's a lot more cost efficient to use the heat from that fluid than from the soil. And that has become a lot more appealing now. And then utilities that handle bulk, high voltage, energy storage components, batteries, fuels, depending on the cost. I share with you a little bit on that. And then electric cars. And then electric cars also, we have done projects. Dr. Sarah Mullen did a great doctoral dissertation on using cars for Minnesota, a very small number actually, 250,000 cars, to keep up the system, to basically get paid when you provide what is called reactive power. And I'm going to use an analogy that my colleagues would hate me if they're power system purists. Think about real power. Please think of it as a glass of beer. I'm having coffee here. It's from my old work. I did that for Georgetown. They have a center on international affairs and so on. Anyway, imagine this is beer. That's what you pay for real power. Reactive power is the foam on top of it. What's a beer without a foam? The bubbles go down. There's no bubbles. So there is no, if reactive power in a power system goes out, electrons don't flow. To have the electrons flow, you need real power plus reactive power. For those colleagues who may be a little bit of math geeks, think of it as an imaginary number, A plus I or J, B, or alpha plus I, beta. Alpha is the real power, is the beer. The foam that keeps the bubbles going is the imaginary component, is the beta. Makes sense? You need both. But who pays for foam? Nobody. But without that, our voltage goes down. We have voltage collapse. So we looked at, Sarah Mullen, Dr. Mullen looked at, if you have electric cars providing that service, what's the cost of that to reliability? And how would it support in St. Paul, in Minneapolis, support the system and sell both real power and provide voltage support? And then neighborhood and demand signs, campuses, and so on. So doing more examples. This is another doctoral dissertation, Dr. Anthony Giacomoni. Actually, this was his postdoc job that he did. And he's at PJM, folks that control the most efficient, if you will, Pennsylvania, Jersey, Maryland, kind of to the east of us. Without them in 2003, we would have had a blackout. That blackout that affected the entire East Coast, Northeast, would have traveled to Minnesota, Wisconsin, etc. So what is a microgrid? think of it as a smaller power system, has several megawatts or less. Typically, it has its own distributed generation, including controllable natural gas, pumped hydro, combined heat and power, biomass, or solar and wind, which you don't know when it's going to be on or off. There has optional storage capacity. It has its own load center, smart autonomous, that can be run automatically like the OATI building by 494 and 100, which is called Smart Grid Campus. That's exactly what is Smart Microgrid. And then can interconnect to the larger grid or operate islanded when the larger grid is down. And in this, cost, efficiency, environmental footprint, and keeping the system resilient are key drivers. So these are typically, we have many of these together coupled. By the way, we have used them in military installations, in schools, in college campuses, including at Illinois Institute of Technology. Professor Mohammad Shahidpour got a really wonderful project, did that for Illinois Institute of Technology in downtown Chicago, worked with Commonwealth Edison to make that into a smart microgrid. Dr. Kaplan, Mahmoud Kaplan, has done a great job again with St. Thomas. Very similar architecture. So those are great examples. But then you have you want to depend what your objectives are. If you want to have full autonomy, if you're running a base for our Department of Defense overseas, we had over 3,000 bases overseas. All of them depended 20 years ago on the local utility plus their own diesel or backup generators. Is that how we want to run our Department of Defense installations overseas? No. So that became a fantastic pilot to actually start this. And then you have interconnection policies that have that you want to minimize line losses, infrastructure cost for building, capex, maintenance, and so on. And then you want to minimize impact of propagation of cascading faults and so on. By the way, footnote, that's why DC microgrids become appealing. There is no cascading failure. And it's much more easier point-to-point control rather than AC, which is path of least resistance, Kirchhoff voltage law, current law, basically which determines which lines the electrons are going to flow through. And then cyber attacks and so on, communication systems are a huge part of that. And fast computations would, like what you saw, to stabilize, have a look ahead, have foresight, be more strategic, even look, I know it sounds crazy, but we can look 10 days, 15 days ahead with over 99.4% accuracy. Seasonal is still a challenge, because we're relying on computational models from national weather organizations and others. So this is basically, you can think of them, you have a transmission high voltage, and locally you have your own generators. It can be any sustainable source. You have your own connectivity among the loads, and loads can be multiple. UM Morris is 22 buildings, for example. And then you have also storage optional in order to do that. This is from my old work. I took a year leave of absence from the U of M a year ago, moved to Quanta Technology in Raleigh, and had the privilege of creating 4 major initiatives for them in the 6 months I was there. And then I was approached to lead Energy Policy and Security Associates, and I decided I like to do that. So I retired from the U. I love the U, by the way. Please support the U. It's the best job I've ever had, which is, it's a very high functioning, smart, capable, huge impact on Minnesota economy and beyond. But anyway, here is maybe too much information, but I survived cancer twice in 2017 and 2019. I went through a period of from 2017 to 2020 injustice within Hennepin County. I felt I don't know how much time I have. Time is precious. I don't want to spend my time worrying about 7 to 10 years down the road my students are going to make an impact. I would rather be in a faster pace that I can help empower others to implement it. And that's what I did. Also, it opens up 1.6, 1.7 new faculty position, tenure track if I step down. And I survived COVID, all kinds of stuff. So for both personal reasons as well as thinking about the impact on others, I decided to retire. But I missed the U big time. It was not at all for any reason other than that. So these are some of the projects my old colleagues, former colleagues have done, and I had the privilege of working with them, especially with Puerto Rico. Luma Energy, which is now empowering Puerto Rico to keep the lights on. But there are many, there are over 70 projects when it comes to microgrids, and some of them are transportation electrification, which is this lighter color, microgrids, and energy storage. Many of them are a combination of all of them. So this is Puerto Rico. This was when it was hit by Maria in 2017, 6 years ago. Thank you, Jason. I love your baseball cap. Thank you, sir. So this was 6 years ago. Almost we are coming up to the anniversary. It took 8 months to bring electricity up to 95% of the island. Last year, unfortunately, they were hit with another one. It took them less than 5 days to bring it to 92% of population. The backbone, the stronger backbone I shared with you, that is enhanced. And by 2030, all of Puerto Rico, it's not going to be running on coal or oil that it did, but it's going to be renewables and microgrids. It's a huge success story from a nightmare, from a tragedy. I had the privilege of working with colleagues when they were attacked. I won't go into details. Most of it was classified. Cyber attacks, national labs, other amazing people were the leads that work with them. But this is the 2 outages that they had in Ukraine by the Russian state agencies that took their system down. It was right before Christmas in December of 2015 and then December 2016. How to make it more not just cyber secure, but also make it more locally microgrid configuration that only one part goes down and the critical parts, hospitals, schools, government centers, etc., remain operational. Closer to home, Colonel Matt Vatter, Minnesota National Guard, he did his graduate degree with me. I had the privilege of creating 2 new graduate degrees at the U for full-time working profession. One is in the security area, one is in medical device innovation. Sorry. He did the one on security after he had gone through War College. And this is what they did in Camp Ripley on the way to the up north. They worked with Minnesota Power, and the size I cannot tell you. It's kind of depends on their confidentiality, but they have a microgrid now in Camp Ripley, and he did his capstone for his Master of Science with me in this area. We are all familiar with this beautiful map from Minnesota Department of Commerce, and you are all familiar with Morris. One of the 5 campuses of the U of M is right here, and it's near the Buffalo Ridge. It's near what some folks call this region in Iowa. For those who are outside of Minnesota, they call it the Saudi Arabia of wind. So this is for the U of M Morris. They had a wonderful chancellor and another colleague who reported to the chancellor, who was the lead on this. They have 2 wind turbines that provide 1.65 megawatts, about 70% of campus's electricity needs. But you see, when your mission also aligns, for UM Morris, sustainability is their stated mission. So it's much more straightforward to say, my mission is sustainability. How many utilities do we know, or how many organizations do you know that in their value statement or mission statement, sustainability is one of them? So that's the starting point. That also helps with clear vision and clear, if you will, like lining up the vectors in that direction, and culture change within the organization. So this is the modeling we did for them. And this is one of my former graduate students and I. We looked at what they had and what they were getting from Otter Tail Power Company. That was a great partner in that area. And then we looked at the choices of what kind of storage, what kind of battery or other system they can use, and what's the overall. I won't go through the technical assessment. With Anthony, we did another project, the overlay of smart grid. So one part was storage selection, optimization of that. The other part was the overlay of sensors and the technologies we used. This is just to show you, since we have a little bit of geek in us, this is showing you the equations for the 4 objectives. We want to minimize outage cost, minimize energy costs, minimize demand costs, minimize capital costs. So load shifting, load scheduling for that. Without our system, voltage would drop, like what I mentioned to you about the beer. You see, this is the voltage sag. And you see that especially if you're running buildings that depend on highly reliable power, this is not harmonics, but it can have harmonics in addition to this that would make power quality problems. But that's different. This is reliability. With our system, optimized system, we keep the voltage up, we keep the system up. And this is the selection for where the microgrid would have storage devices. We assessed about 24, maybe depending on what the choices were, storage technologies, and it ended up being 5 tiny microgrids within the system, because all buildings are not created equal. Some have different electricity needs, must run all the time, and so on. Good news is when we optimize it in the method that you saw, that nonlinear stochastic optimization, we end up with how much we are saving, and the cost recovery. You would have, solar panels takes 8 years, 15 years. For this, it takes you less than a year and a half. In avoided outages, better. We didn't even put reliability in terms of power quality, anything. This is just avoiding outages. And the differential cost of buying it from Otter Tail Power or not buying it, you recover the cost quickly. System performance, these are the 3 key performance indices used for distribution system. They're called SAIDI, abbreviation, SAIFI, and KD. The lower, the better. So substantial improvements, a number of people in those buildings, not students, but these are the permanent employees and faculty and so on. And then the KD remained about the same. On the other hand, this is thanks to my colleagues at Morris. This is showing you the carbon footprint. I think Tim, many colleagues, maybe Jason, have seen this before. This is showing you the net CO2 footprint in metric tons. Metric tons is measured here in yellow line. After the first one, look at it, it went way down. After the second one, it went even more. So currently, we don't have carbon pricing. But allow me to ask you, this cup of coffee, if I didn't know how much the coffee is, or you don't know how much it is, would you buy it? The father of modern management science said, you manage what you measure. I would add to it, that's a prerequisite. If you price it, you value it, you manage it even better. So how can we manage it if we don't price it? What is the price incentive? What's the price feedback into our system? It's not just watts, dollars and watts have to be included. And then within that, carbon footprint. So this, I'm not going to bother you too much. We did extensive analysis for this, including to improve the reliability, at what cost, trade-offs, etc. Morris, which at the time we were going to build a 30,000 community commercial residential, was another project we did pro bono. These projects we did pro bono for the U of M without any grants or any funds. It was my grant from National Science Foundation that I justified that we are helping our community and we are going to test them on these communities, basically. So this ended up being a combined heat and power, the best, most optimized design. This became 4 capstones for 4 of my Master of Science in Management of Technology, MOT, my former institute. And they were amazing. They had 12 years of experience on average between 4 of them. Honeywell, what's the car that James Bond drives? He's from Scotland. He worked so we had great one, an army veteran, wonderful colleague, amazing one from Medtronic who wanted to go get into one from 3M. And it ended on each one became the CTO, one became CFO, one became COO, and one became the kind of a general manager. That's the roles they played for their capstones. And they each had integrated was basically that. Another project, we took the dirtiest building at the U of M, most polluting, and I worked with the U of M facility management 2 colleagues ago with Mr. Malmquist, dear friend. And the gentleman who reported to him became the VP at the U. He just left, I believe, this past year. Great people, Mike. We turned that dirtiest building into the cleanest building at the U. So, but these are some of the challenges. To share with you the challenges, how do we are uncertain about when the wind or solar is going to be, even with weather predictions, so on. Still, we are good about 10, 12 days, and you have seen this in the accurate prediction within even 5 days where the hurricanes are going to hit recently. We have better models, but still huge. Energy, you saw that storage, distributed generation, we have done quite a bit. We can handle it, plug-in hybrid or plug-in EVs. We can do all of that. And then security of this is another part. These are the challenges, lessons learned, so that I can conclude it. The big lessons learned are about 4 slides. One is the biggest challenge you hear about these microgrids is how to bring all these sources, solar, wind turbine, either rooftop, smaller modular, looks like a DNA helix, you may have seen them, and storage together is challenging because distributed energy system should be connected to the microgrid with controls at each one, basically, at the building level that can handle it. Other one is power quality. For high-end electronics, that's you're going to need a better system for that. Energy storage, you saw some of the choices. There's a lot more in that area. Another huge area is control and protection, instrumentation, to regulate the power flow, to avoid overloading imbalance, and then protection to detect and isolate faults or abnormalities to prevent damage. Optimization, again, you saw a little snippet of that today, control algorithms, and then managing inputs and outputs within the system to have stable voltages, frequency levels, etc. Other parts, cybersecurity remains a challenge. We have addressed that, but adversaries for various objectives, they always are advancing, and it doesn't require anybody with even a degree in computer science to do it anymore. A lot of the tools are available online. Islanding, connect or not connect, and also standards. Standards are a huge part of it. The other, to wrap this part up, is environmental consideration. They can have huge environmental impact, emissions from the DER, noise pollution. You have seen some of that about wind turbines, killing birds and so on. Even folks in Cape Cod, Hawaii were hesitant because of killing birds and their views. Land, so smaller, more modular, if it is gone through the system optimization, is a lot more appealing. CapEx, basically, maintenance monitorings, regular maintenance monitoring. In Sinai, my colleagues put solar panels. Bedouin destroyed them, broke them for 3 reasons. They wanted to remain connected to Egypt, to be connected to the Egyptian grid and not isolated. Number 2, in a desert, you don't have windshield wipers to clean those solar panels, so efficiency would go down really fast. Integration, it should be very carefully designed. We have some standards for connectivity within IEEE, within other organizations, but you still need to optimize it the way you saw. even for data centers, I've done quite a bit of work in that. Non-engineering regulation, policy, there are no real incentives in Minnesota. That's one of the areas I would recommend for you to consider. I'm at your service pro bono to support you if you go in that area. I've done quite a bit of work in that. Business model to show the economic benefits, and then communicate. These are the three I think you can really help. And I put it on one page so you can see it. So non-engineering, we need really a holistic understanding. The two summary pieces I wanted to share with you are these two. So it's a systems approach, but hands-on. Allow me to fast forward from this. And this is not just about microgrids. It's actually about much more. If you're interested, there are many references I can refer you to, a couple of them that I have in this area. One of them is moving from central power, asset management, as microgrids. And this is, believe it or not, this is from 2014. So it's 9.5 years old. So it's nothing new. Another one, a year later, how to save assets, to protect them, connect them, and so on. And then we did this for, since there isn't much success, wasn't as much success, I thought, what can we do globally? At the time, I was chairman of IEEE Smart Grid, so we partnered with the largest manufacturing in India in 2015. We had the largest technical conference in the history of, as far as we know, IEEE and elsewhere over in India. And these were what we focused on, because we felt that we could put a dent more in that area than here. So here is the part that you're seeing. It's about the mission, if you will. The mission was really how we can help convergence of these to create a more functioning, inclusive society with minimum footprint on the environment, but using their capabilities that they have in IT to enable this transition. When I became chairman of IEEE Smart Grid, we did a comprehensive assessment. These were my recommendations, summarizing everybody, all the input we had. There were 5 areas. That's not going to surprise you, similar to the briefings I gave to the Congress. Develop a robust system, increase power energy efficiency, integrate renewables and distributed power, electrify transportation, promote new customer-focused energy business models. Because at the end, it's about people, prosperity, and our planet. And this slide, believe it or not, is 12 years old. So as you heard a lot in the last hour and 10 minutes, my apologies, I talked too much. I really planned, I thought it's 40, 45 minutes, but it's way past that, so I owe you. Next time, if you invite me, you give me a chance to redeem, I will shorten it more. I will, instead of 40 minutes, I talk 10 minutes. So when you step back and think about Minnesota, what do you think in the areas we talked about we can enable? Take, let's say, Duluth, take Rochester, take parts of St. Paul. A good friend of mine, James Staples, who runs Renewable Energy Partners, I met him where he was a Humphrey Fellow. He has a project in North Minneapolis on Plymouth that he trains people, and he's trying to build a microgrid. He would be a good connection. And there are other things we can do. Start with smaller projects, but have in a sense, start local, but have a much more regional, state vision that we can enable. That's what I would suggest if I can be of service to you. Again, I'm re-quoting Father of Modern Management Science. My hat is off to you because you're trying with a good heart, with sharp minds, focusing on your vision of what Vice President Al Gore, also I fully respect him, what he tried to do or is trying to do even to this day. Quoting management guru Peter Drucker, 3 things happen naturally in organization: friction, confusion, and underperformance. Everything else requires leadership. So my hat is off to your leadership, that you're trying very hard to make this happen. And my question to you is, What can I do to support you? These are what we do in my organization. But you saw parts of the work we don't do in my organization that I did at the U of M. As a professor, I still have 2 remaining doctoral students. They both work in industry to help them wrap it up. One of them is in California, outstanding gentleman. Another one in Siemens off of 394 here in Minnesota to finish up their doctoral dissertations. And thank you so much again for the opportunity and the honor to present you.
All righty. Thank you, Dr. Amin. Everyone, a round of applause.
That's okay. Thank you. Questions?
We had a couple of questions in the chat. I wonder if we can just kind of go through these quickly. Yeah, we are a little over, but I kind of wanted to go to Tim Nolan had an observation. We're still living in a 20th century electricity system. We're far behind establishing microgrids and microgrid technologies. So I guess why are we so far behind, and what do we do to accelerate those systems?
Great question. Thank you, Tim, for asking it. Basically, there are 3 things. One is technology has been on the shelf for about 25 to 30 years to do it. And we called it at the time when I was at EPRI, local area grids and microgrids. We did it for city of DeKalb, Illinois, because we had a mix of things. We could do it. We did microgrids for campuses, for industrial park. Not just we. Globally, there were many projects. So that was one. The trilemma of sustainability, population, pollution, and poverty is now even more important. To address trilemma of sustainability, we need to do better use of our energy resources. With climate change at the rate it has been going, accelerating, it is another big area. So I would say technology was there. However, awareness, utilization, and there was no need to change it. There was no requirement to actually make it into a requirement or incentives for that. That's one. Second one is the trilemma of sustainability. The last one is supportive public policy that would enable this transition from mostly central into distributed. So that actually is a great question. What I would say, I prepared more slides for you in more than what I had, but there are 3 things in addition to the beginning and what we talked. Politics, who gets what, how much they get, when they get it, that part is huge. Economic factors, job creation, pricing carbon, pricing greenhouse gas emission, etc. Technology is pretty much there. It's a question of challenges I shared with you. We got to move the ball when it comes to policy. That is, smart policy takes all of these into account and then doesn't command it, but incentivizes and co-funds 50% government, 50% industry, or 25% government and 75% industry incentivizes that in order to do it. Good news is that part is already underway. That's why I moved to industry to create the initiatives. 2 of them, one big one was on how I was worried that many utilities may not be prepared to handle the money that is coming out of Infrastructure Investment Jobs Act effectively, and a lot of other large organizations would try to get in. So I was very blessed that I worked with colleagues at Quanta Technology to create that, to actually help bring this type of capability to help them as a catalyst, partner 50% from the utility, 50% from the federal government to go for this funding. The other one that is not coming out is IRA, Inflation Reduction Act. So we are in a good place to make this happen. I hope I answered your question, Tim.
Alrighty. Well, I think we'll have to wrap it up here. We're at about 90 minutes. Doctor, I might send some of these questions to you offline and then add them as part of the either the video or the presentation.
Thank you. I'd be happy to answer them concisely and briefly and send them back to you. Thank Thank you.
Yeah, thank
Oh, I
you.
see the questions. I put them on my screen. Energy storage is huge. Just quickly answering Tim's
Sure.
question. Huge. It can be a deal breaker. Depends on the location, the kind of load you have. But if you're running what we typically run, commercial, industrial, residential, etc., and you want zero outages, what my former boss Kurt Yeager used to call perfect power, you're going to need to have storage. Sorry. Thank you. Thank you very much, sir.
Thank you, Dr. Amin. Our next chapter meeting will be on Thursday, October 12th at 6:30 p.m., when our guest will be Michael Reese from the West Central Research and Outreach Center of the University of Minnesota Morris. Michael is the research lead of green ammonia, a fertilizer produced without fossil fuels, so be sure to join us. And on behalf of the leadership team here at the Central Minnesota chapter of the Climate Reality Project, thanks for attending.